Section 7.1 is going to talk about creating a confidence interval for population proportion. And to start things out, what I had you do was go to that website, random.org, press the button continually, and then try and find, what percentage of the time that you ended up on land versus on the ocean. And from this, I'm hoping we're going to get an estimate of the percentage of Earth's surface that's covered by water. So let's take a look at some of the results here. And that's right here. Here's your results. Got some percentages. I guess I can get rid of these two values here. But overall, values are all over the map, from a low of, it looks like about 63% to a high of 83%. Wow. Do you think any one particular value that we got here is spot on? You think it's that somebody just nailed it? Actually, it looks like somebody did, which is kind of cool. But for the most part, these aren't going to be exactly spot on. Let's remind ourselves of some things here when we're talking about sampling, and that's what we're doing, is we're sampling from the Earth's surface to try and find the percentage of its surface covered by water. Our goal in sampling is to find out some information about a population. In particular, a population parameter is what we're trying to find out about. The population parameter here that we're going to work with is the population proportion. Let's remind ourselves of some of these notations. What do I use for the sample statistic? What's my notation for the sample statistic when it refers to the population or to the sample mean? What symbol does that use? X bar. Thanks, Jaslyn. What's its corresponding population parameter? What does it estimate? Mu. Nice. Let's move down to the sample standard deviation. We represent that with a S. And over here with sigma. So a couple Greek letters. We break that trend with the population proportion. Population proportion is a P. What estimates that population proportion?
P caret.
Yeah, P hat, P caret, P chapeau, if we're in France. But P hat, that's our estimate of the population proportion. So what I had you do is calculate a bunch of different P hats. You all got different estimates of that P hat. Is it likely that your particular value is exactly right? No. I think there were a couple in there that were exactly right, but for the most part, they were off a little bit. And you know ahead of time that by sampling, you're probably not going to get the exact right value. So what could you do? If you wanted to give somebody an idea of how close you think you are or could be to the correct value, give yourself a little room for error, right? You say, well, could be a little higher, a little bit lower. And that room for error is your margin of error. And that leads to something called a confidence interval. So what we're going to do is we're going to try and guess what P is. And we know we're not going to get it right on. Our best guess, P hat, this is what's called a point estimate. That's a vocabulary word that you probably should be familiar with. Not that I'm going to test you on an exam saying, oh, what's the point estimate? Although I could. But you will see that in some of the homework problems. They'll say, well, what's the point estimate of the population proportion? So that population proportion, we don't know what it is, but it's probably somewhere close to P hat, maybe P hat plus a little bit, so plus an error term, or P hat minus some error term. That's going to be our confidence interval. Now, one more reminder thing in terms of creating that confidence interval. One of the things you're going to need, if you were to do this by hand, is E is going to be Z sub alpha over 2 times the square root of P hat, Q hat, all over N. Boy, that's a lot of stuff here. Fortunately, you're not really going to have to work with that directly. But I do want you to know what Z sub alpha is. Let's remind ourselves what Z sub alpha is. That's notation that we went over in chapter 6. Can anyone tell me what Z sub alpha is? What's that mean? Yeah.
Z-score of the area to the right.
So it's the Z-score that corresponds to the point on the Z distribution with alpha, the area in the right tail. So this is your Z sub alpha. Awesome, thank you. Now, you can get that from Google Sheets. You would have to just type in the proper command. You type in, what is it, norm inverse, and then you have to type in the area to the left to get that point. But whatever. Fortunately, you don't have to work with that too much directly. But let's work with what you do have to do directly. And this first little bit is going to be trying to get you up to speed on some of the notation that we're going to use when we talk about confidence intervals for these kinds of things. So we've got a magazine that provided results from a poll of 500 adults who were asked to identify their favorite pie. What's your favorite pie? Anyone? Apple? Yeah, apple comes to mind. Chocolate would not come to mind when they're asking me about their favorite pie. But 14% of those that answered this poll said chocolate pie. So we're going to create a confidence interval for the proportion of people who think that chocolate pies are the best. Now, like I said, there's some notation here that we want to get familiar with. Let me start with the easy parts. So let's start with N. N is the size of your sample. And let me zoom in here. That's your N right here. So that's N. Try it out. Let's try this one. So that's N. So 500 adults were asked to identify their favorite pie. Among the 500 respondents, 14%, that's your p hat. Now usually they don't give you p hat. Usually they give you some information to calculate p hat. But this time they gave you p hat. Zoom up. There we go. That's your p hat. P hat is typically calculated as x over n. It's usually not just given to you like this. Now, in our case, they didn't give us x. You'd actually have to figure it out with a little bit of algebra. It's pretty easy. You multiply 500 times 0.14 and you'll get 70. So x equals 70. That's not actually given to you. You would actually have to calculate it. And then you would get your p hat. P hat is x over n, 70 over 500. There's also a q hat that's going to be part of our work. And you can think back to binomial random variables to try and figure out what q hat would be. If you have p hat, how do you think I'm going to get q hat?
1 minus p hat.
1 minus p hat. Perfect. 1 minus p hat. Nice. Our margin of error, that's kind of a complicated term. I put that on the front side of this. Or right here. Like I said, you're not really going to have to get your hands dirty to calculate that, but I am going to ask that you work a little bit harder in a different respect. So that's going to be your margin of error. Our margin of error in this particular case was 5%. So let's see. That's right down here. Plus or minus 5 percentage points. That's your E. So they've already done all the calculations for you and determined what E is. There's one last thing that we have to figure out, and that is what's the value of alpha. So that's down here. What's the value of alpha? And the value of alpha is going to be kind of the complement of what the level of confidence is. So alpha equals 1 minus the level of confidence. So if alpha is, or excuse me, if our level of confidence is 99%, then alpha is going to equal 1 minus 0.99, or 0.01. That's your level of alpha. Not that we have to worry about it, but what you would use alpha for in this case is actually figuring out what that error term is. And the part that alpha plays is figuring out this part right here. Figuring out the point in the right tail with alpha divided by 2 of the area in the right tail. So that's where the alpha comes into play. For us today, that's just going to mean we're just going to have to enter in the level of confidence. So it makes it a lot easier. The one thing that I am going to ask though is that you're a little bit more careful about stating your conclusions. And I'll talk about that in a second. Let's move on to our first example. Are you okay with all the notations here? I think we covered everything here. And let me just remind you that p hat, that's your point estimate. That's your best guess. But we know our best guess is going to be wrong, or is likely to be wrong. So what you're going to do is surround it by a confidence interval. You're going to do p hat, and this one is dead. Let me grab this one. P hat plus or minus some error term. That's going to be your confidence interval. Okay. Let's take a look at the first one. Example A. Questions or thoughts on the notation? Comfortable with that? Homers, zoomers? Okay. Let's go to example A. Use the sample data and confidence level below to complete part A through D. A Research Institute poll asked respondents if they felt vulnerable to identity theft. In the poll, 1,020 respondents, 590 of which said yes. We want to use a 90% confidence interval or 90% confidence level to answer all these questions. So the first one is find the best point estimate of the population proportion P. Well, the best point estimate is the number of successes, which is your X, divided by the total number of possible, or total sample size here. So what are those numbers for this particular problem?
590, 1020.
Yeah, 590 and 1020. So P hat is going to be 590 over 1020, which should be a little bit less than 58%. Let's take a look here. 590 divided by 1020, 57.8%. So 0.578. Okay, looking good there. Identify the value of the margin of error. All right, well, this is the part where we're going to let statistics or let our StatDisk package help us out a little bit. So let's open up StatDisk on our computers. Let's see. I guess I don't have it open, so let me open it up. Oh, no, here it is. There we go. Once you open up StatDisk, you're going to want to click the analysis menu. And if you look down a little bit, you'll see confidence intervals. Click that submenu, and that should open up something else to the right. You want a population proportion one sample. So that's that first one right here. Don't worry. By the end of the course, we'll do all these different parts of the submenu. Right now, let's start out with population proportion one sample. That's going to take us to a confidence level. What confidence level do they want from us here?
90%.
90%. Good. So change that to 0.9. All right, let's keep going. What was the sample size here? 1020. And of those, how many successes do we have? 590. Now there's one tiny bit about the output here that I'm not really sure I'm fond of, but let's just work with this. So it gives you your margin of error, which is 0.02543. And it gives you your 90% confidence interval. It's this one you want. We're not going to use the Wilson score confidence interval. My guess is it's a non-parametric test that we're just not going to get to. So this is the one that we want. But in particular, in answer of their questions, they were asking, well, what's the margin of error? And that's 2.543% or 0.02543, whichever one you want. So identify the value of the margin of error. E equals 0.02543 or 2.543%. Okay, nice. Saved ourselves a lot of work there. Construct the confidence interval. Well, all right, let's do that. Actually, let's let StatDist do that. And that's between 0.5530 and 0.6039. So 0.5530 is less than P is less than 0.6039. So we're not sure what the value of is if you were to try and talk to everybody that's part of this population. Our best guess is that about 58% of people are worried about identity theft. But where the true value is probably between here and here. Now, I was being a little bit loose with the way I stated this. So we are going to have to sharpen up the way we state our conclusions. I'm not going to just be looking for just anything when we look at the conclusions to this kind of thing. So let me give you a nice generic form, kind of a fill in the blank of how I want you to state your conclusions. So I'm going to write that on the back side here, right down here. We can be blank percent confident that the true population proportion bless you. And I want that described a little bit, is between blank and blank. That's the way I want your conclusion stated. I want you to stay away from the use of the word probability when you're talking about your conclusion. And I'll go back and explain why in just a minute. But let's see if we can adapt that and state our conclusion for this particular problem. So, let's see, 3 up here. Let me try and state that in words. So, in words, let's see, we want it to be, we can be 90% confident that the true population proportion of people worried by identity theft is between 55.3% and 60.4%. So I rounded an extra decimal place there, but that's okay. This is pretty much exactly how I want your conclusion stated. It's just cookie cutter from that form that I gave you on the back side of this page. I want to see the level of confidence. I want you to talk about the true population parameter that you're working with. So in this case, it's a true population proportion. That way it distinguishes that you know the difference between a sample and a population parameter. We described it. People worried by identity theft. And then finally, you gave me the correct intervals. On a problem like this, maybe this is an 8-point problem, 4 points are going to be given towards giving the correct conclusion, writing it correctly. So I've made it a lot easier for you to come up with these numbers, a lot easier. So I am going to ask a little bit on the back end, and that is you're very careful with wording your conclusions. This is the most important part. You've got to accurately describe what's going on to somebody who's going to read your stuff. I mean, you don't just do this stuff for your own curiosity. Presumably you're doing this stuff to hand off the results to somebody else, and they have to be able to understand it. All right. Are we okay with our conclusion here? Let me go back and talk about something I said just a moment ago, and that is, I don't want the word probability or chance anywhere at all in your conclusion for a confidence interval. And that's because there really is no probability in the way you would think. Let's go back to the way we started this, and that is with our random points here. I had everyone find at least 30 random points on the surface of the Earth and calculate what percentage of the time you were actually in water. And here's all the results. Now, the true value, at least according to Google, is 71%. So let's see. If you were to construct some confidence intervals here, and let me just copy the correct formulas down here, get rid of a few. Divides by zeros. And then let's copy these as well. Let's find out how often our confidence intervals actually contain the true population proportion. So the true population proportion was 71%, and I noticed that there's one group that actually hit it exactly, so cool on you, but a lot of other ones missed it. But did your confidence interval capture that? Well, this one did. This one did. This one barely did. This one's like really wide. So what that confidence level represents is confidence in the procedure. What it says is that 90 times out of 100, this procedure will contain the population proportion. Is it guaranteed to contain it? No, can't guarantee it. If you want to guarantee something, go to a math class. And statistics is the art of never having to say you're sure. No, honey, I'm pretty sure that I wasn't unfaithful to you, right? I'm not sure how well that would go over, but in any case, we can't say that we're sure. We can say we're pretty sure. We have confidence in our procedure. But once the data is collected, this is no longer a probability that you would think. This either does or does not contain the true population proportion. So if you wanted to assign a probability to it, it would be 0 or 1. And we don't know which. It either contains it or it doesn't. But there's no probability that's associated with this. All right. Looks like all our confidence intervals did contain it. That's assuming that I calculated this correctly. And I'm looking at some of these and they look pretty wide. I don't know that they would, but all right. We'll leave that there and go back here. Questions on example A? We doing good there? Chloe?
Yeah.
All right. Philo? And got one more coming in late. Let's get you in. All right, let's try another one. Let's try example B. So let me go back here, example B. Use the sample data and confidence interval given below to complete parts A through D. A drug is tested to help prevent blood clots in certain patients. Clinical trials amongst 4,584 patients treated with the drug. 189 develop the adverse reaction. Construct a 99% confidence interval for the proportion of adverse reactions. So, okay. The one thing that StatDist doesn't give you is this actual proportion, the point estimate. So how do you find part A? What's going to be your answer there in part A? X divided by n in this case is which numbers? 189 divided by 5,000 or 4,584. So that's going to be your p hat. So let's put that down. So p hat 189 divided by 4,584. That's going to be about 4%. Let's just get a number here. 189 divided by 4,584. Yeah, oh. 0.0412. Okay, not bad. That's all the calculation we're actually going to have to do for ourselves. For the rest of this, it says identify the margin of error. Well, where are we going to get that from?
From StatDist.
StatDist, yeah. We're going to make our life a lot easier. We're going to do it with StatDist. So, there's StatDist. What have we got to change here? What's our confidence level this time? 99%. We had 4,584 people in our trial, of which 189 developed that adverse reaction. I'm always kind of bothered by the fact that they call that the number of successes. I don't feel like celebrating that they got an adverse reaction, but we'll let that part be handled by the English department. When you click this, you get a margin of error. You tell me, what's our margin of error?
0.00.
Yeah, good. 0.00756. That's pretty tiny. That's less than 1%. So that's a really tiny margin of error, and I'm going to go back and talk about that in just a little bit. Let's see. Construct the confidence interval. Well, that's already kind of done for us. So it's just a matter of copying those numbers down. That's going to be between 0.0337 is less than P is less than 0.0495. So that's our confidence interval. And I rounded it to the 10,000th instead of going all the way down to the 100,000th. All right. Now, here's your job. And I'll ask the people on Zoom to put an answer in the chat. You guys can figure out which statement regarding the conclusion is correct. And I've got them numbered up here, 1 through 4. Take a moment and think about it. And then compare your answer with a neighbor. So let me let you think about it for a few seconds and then ask you to compare with a neighbor. Which one of these 4 seems to be the best? All right, compare to a neighbor. Talk to a neighbor. Let's see. I'll mute things here so you guys can just chat amongst yourself on Zoom. Didn't see anyone put anything actually in the chat. But you guys can talk to each other on Zoom. Sort it out. Which one of those four do you think looks like a winner?
Similar, but I think.
All right. So let me take a look at the chat here. Okay. Let's do a little straw poll here. See what you guys think. So first of all, how many people like number 1? 2, 3, and there's about 3 or so people that on the chat that think number 1 is good. How about number 2? Nobody. No takers for number 2. How about number 3? All right, looks like it's 1 or bust. Number 4? All right, 1, 2, 3, 4, 5, 6, a lot. All right, so a lot. Cool. All right. Well,
numbers here.
yeah. So a couple of you, I think I heard your discussion, noted the fact that this talks about a chance. And statements about probability and chance and likelihood like this do not belong in your conclusion for a confidence interval. It's just wrong. Because the only probability here is 0 or 1. If you really wanted to mention chance, the probability that this contains it or doesn't is 0 or 1. And we don't know which. That's the only probability that works here. 99% of sample populations fall between there. That's not right. That's not what's going on with these things. You're talking about a confidence interval for the population proportion. So the last 2 look most attractive, and a lot of you honed in on the correct one, which is number 4. So winner, winner, chicken dinner. Nice. Number 4. One has 99% confidence that the interval from our lower bound to our upper bound does contain, and notice there's a little thing in here that I like seeing in your conclusions about a hypothesis, or not a hypothesis, but a confidence interval, the true value of the parameter. I like seeing that word true. That's kind of saying that we don't know what the true value is, but we're trying to estimate that. We don't know what the parameter is. We're trying to get at that. Nice. Nice. Let's try example C here. And let's look at it here. A little easier, I think. A genetic experiment with peas resulted in one sample of offspring that consisted of 445 green peas with 154 yellow peas. Construct a 95% confidence interval to estimate the percentage of yellow peas. Part B, it was expected that 25% of the offspring peas would be yellow. Given that percentage of offspring yellow peas is not 25%, do the results appear to contradict expectations? So, all right, lots of things we got to work on. First part of it, though, is figuring out what p hat is. That's something I could ask you for. And what I want to draw your attention to is that we had 445 green peas and 154 yellow peas. So how would I calculate p hat?
154 over
154 over Well, it's not just over 445.
Add them.
Yeah, you've got to add those, right? Because you want to look at the total number of P's here. So it's going to be 445 plus 154. So it's going to be 154 over 599. That's about 25.7%. Okay. But keep in mind, that's just a point estimate. Do you think this is exactly the true population proportion?
No.
Probably not. So the best thing to do is to surround it with a little confidence interval. Give yourself some room for error. Chloe?
So would we put N as 599?
Yep, that's your N. So N is 599, that's your X, and that total is your N. Yep. The other thing I guess you need to take note of is the level of confidence in this case, and that's 95%. So let's take that information over to StatDisk and see what StatDisk has to say. And then we'll actually conduct another little experiment. So it's kind of cool that we actually get to experiment with math. How often do you get to do that? I know you're thrilled. Contain your excitement though. Let's see. StatDisk, here we go. We want a 95% level of confidence. Sample size was 599. Number of successes was 154. Bam. So our margin of error was 3.5%. We're not actually asked for that in the problem. It just wanted us to find the confidence interval. So let's take a look at that. That's going to be between 0.2221 and 0.2921. I rounded to the nearest 10,000th in each of those. Now I'm putting P between these things because that's what we're trying to estimate. You're estimating with P hat, but you're trying to get this. We don't know what it is. So we're saying it's probably between here. And we have 95% confidence in our procedure. Let's answer part B before we practice writing this conclusion in words. Given that the percentage of offspring yellow peas is not 25%, do the results contradict expectations? Well, we got 25.7%. Does that contradict our expectations? Are our expectations wrong? Is their theory wrong? Philo, what do you think?
I don't think it contradicts it, because it falls within the range.
Beautiful. Yeah, it's not a contradiction because that value falls within our range, the range of our confidence interval. So, yeah, we're saying, all right, this is our best guess, but you know, it's likely that the true value is between these two. And 25% is between those two values. Awesome. Thank you so much. Let's state our conclusion in words here. So let's do example C. And I want you to state your conclusion in words for this. Who wants to give this a shot? What's your conclusion in words going to look like? Test it out now. This is free. There's no points taken off your exam if you test it out now. Victoria?
We can be 90%, 95% confident that the true population proportion of yellow peas is between, is between 22.2% and 29.2%.
Beautiful. Wouldn't change a thing. We can be 95% confident that the true proportion, or you can say true population proportion, either one. True proportion of yellow peas is between 22.21% and 29.21%. So, beautiful. It's exactly the way I'd like to see it stated. Are we okay with that conclusion? Cameron, what do you think is going to happen to my confidence interval if I change the percentage here? If instead of being 95% confident, I want it to be, say, 90% confident. How do you think that's going to affect my interval?
Is it gonna shrink?
It's a good guess. Is it going to shrink? Let's find out. So currently we've got between 22.2221 on the low end and 0.22 or 2921 on the upper end. So this is what our current confidence level looks like. And this was what, 25.7% in the middle. This is for a 95% confidence interval. Let's see what happens to a 90% confidence interval. So this is where you get to experiment, which is kind of cool. You don't get to do that in a math class very often. So now we get 22.77% or 22.77. So let's do that here. What happened to our confidence interval? Was Cam right? Did it shrink? Is it not as wide?
No, it goes up because you're including, like, you need 90% to fall within that.
Well, 90% of the time we hoped to be right with this. Now, I'll tell you what, let me do one more. Let's go up to 99%. And I think this should make a dramatic difference. Let me copy down this other number here, 0.2865. So looking at things here, graphically, this was our 90% interval. If you want to be more confident, you've got to give yourself more margin for error, right? So that means your confidence interval is going to get wider. If you don't care as much, if you're like, oh, I only want to be 90% confident, then your confidence interval can shrink, and it will shrink. So what do you think is going to happen when I look at 99%? Where's that going to be relative to what I've got here? It's going to be even wider. All right, so let's take a look at what happens at a 99% level of confidence. And now it's at 0.21 and 0.211, 0.2111, and 0.3031. So that's that last kind of interval that we can look at here. Actually, we can look at it as many as we want, I suppose. But the more confident you want to be, and the more confident you want to be in your conclusion, the wider this is going to be. So that's your 99% confidence level. Cam?
Is the lowest possible confidence level 50% because it's either at 50%, it's either yes or no?
No, it doesn't quite work that way. Your level of confidence is going to influence the error term, which is E. E is Z sub alpha over 2 times the square root of P hat times Q hat over N. So quiz on that on Monday. LOL, all right. But basically, this is going to decide the size of your error term. If you look at the size of our error term here, it's 0.46. That's pretty big. When we first did this with a 90, let's see, let me just do a little chart here. 0.99, 0.95, and 0.90. Our error term, 0.460. Let's see what it is with 95. 0.35 or 3.5%, and then down to 90%. 0.29. So when you look at the size of your confidence interval, this is your level of confidence. If you want to increase your confidence interval, you're going to increase the size of that error term. So if you were down to 50%, that's not going to mean this is down to 50%. It's just going to mean it's a lot smaller than it is now. Yeah, it's kind of an interesting question. What would happen?
I was just saying you couldn't go below 50.
Well, here's what's going on. You're not taking your point estimate. You're not adding 50% and subtracting 50%. You're adding and subtracting the error term.
Yeah.
And so that's different than the 50% level of confidence. You're not taking, plus 50% and minus 50%. You're taking plus the error term and minus the error term. So those are a little bit different. But you got me curious here. What's going to happen if we put in a 0.5? This is probably going to be really small. Yeah, so now you're down to 1%. So what that would mean is that half the time, this interval will contain what it's supposed to. That's what it means.
Okay.
So, good question. Now, if you look back at some of our early examples, then let's look at the size of the error term that we've encountered. Our first error term was this one, about 2.5%. The second error term was a lot smaller, less than 1%. That gave us a very narrow confidence interval. That means our confidence interval was, less than 1.5% wide. That's pretty good. You're really being precise about what your confidence level is. So what made the big difference between this and this one? I mean, if you were conducting some polling results, you want to know if you're ahead of a candidate or not ahead of a candidate. This tells you a lot less than this does. Here, boy, that's a tight range. Here, the range is like from top to bottom, that's 5%. That's a bigger range. What makes the difference is your sample size. Here, we had a sample size of 1,020. That's not too bad. A lot of times they'll do national polls with, 1,000 or 1,200 or 1,300. But how about down here? We had a much bigger sample size. And that much bigger sample size gave us a much smaller confidence interval, narrower. And that's desirable. So what if it was important to you to control the size of your error? If you said, you know what, I gotta know, because I'm in a tight race with, my opponent, I gotta know where I'm at. So I have a 1% confidence, or I want an error term of 1%. You can figure out the sample size you would need if you wanted to get that confidence interval to as narrow as you want, to whatever error term you want. So let's look at our sample size calculation, example D. So you're the operations manager for an airline, and you're considering a higher fare level for passengers in aisle seats. Yeah, bad idea. How many randomly selected passengers must you survey? Assume that you want to be 99% confident that the sample percentage is within 5.5% of the true population percentage. Complete parts A and B below. Well, that 5.5%, that's your E. So let's kind of note that for ourselves. That's E. E, 5.5%, which is, as a decimal, 0.055. Make sure you move the decimal places 2 places to the left, not just 1. And we want to be 99% confident. So that's our level of confidence. Let's take note of that as well. Now, in old days, you'd have to look up this value, z sub alpha over 2 from the z table. Then you put it into this formula along with E and then grind it out. Fortunately for you, I live in the 21st century, not in the past. We're not going to do this with the old method. We're just simply going to go up here. Analysis. Sample size determination. I've got 3 things I could choose from. We're estimating a proportion, mean, or standard deviation. Which one sounds right? Proportion. Yeah, proportion. So our level of confidence, we want it to be 99% confidence, so we'll put in 0.99. Margin of error was 5.5%, but you got to put that in as a decimal. Now in this case, they didn't tell us any estimate of p hat. And we don't know the population size, so we're just going to leave those blank. When you press the evaluate button, you should get 549. Yay. But sometimes you could know a little bit about this problem ahead of time. And so what happens if you know a little bit ahead of time? Well, let's take a look back. Assume that a prior survey suggests that about 36% of air passengers prefer an aisle seat. So, I don't know, I always like the aisle seats, but. So in this case, you've actually got an estimate of p hat. What should I type in here? Grace? 0.36. Again, you got to put it in as a decimal. But now when you click evaluate, you've given it a little more information. You don't need as big of a sample size. Your previous sample size estimate was based on the assumption of a worst case. But if you don't have the worst case, then this time we're going to get, where is it, 506. So there's 2 different cases for our sample size calculation. Just kind of depends on which one you need. Whew. All right. What do you think would happen to my sample size calculation if instead of making this 5%, what if I made it 1%? How do you think that would change things? Am I going to need more people or less people to have a narrower interval?
More people.
Yeah, probably a lot more people. So we're going to go from 506 up to 15,000. Wow. Yeah, if you want to be that certain, good luck. I hope you have a big budget in your research department, because that's going to take a lot of work to get that many people in there. So, but, I mean, you can, just kind of depends. And if you don't know any of this prior information, that number is actually going to get worse. 16,588, so. Any other comments or questions on section 7.1?
So when we were on status, how come you changed it to estimate proportions?
How come I changed which?
That to estimate proportions instead of what we were using earlier. Like I was saying, estimate proportions in the top. It's different analysis earlier.
So you go to analysis, sample size determination, and then estimate proportion.
So it was different earlier, so I didn't have the estimation of the P and population size.
No, because before we were using a different menu. Before we were doing a confidence interval. This time we're doing things kind of backwards. We're saying, this is what we want our confidence interval to look like. We want an error of no more than 1%. So when you look back at our previous confidence intervals, like these, we had different confidence levels that gave us different confidence intervals. So here our confidence interval had an error of 3.5%. Here it was more like 4.6%. If you wanted to control this and say, you know what, I want my confidence interval to be, within 1% or 2%, whatever, then you're going to go to a different menu on StatDisk. So instead of doing a confidence interval, you're going to do a sample size determination. And that's what took us to that second menu on StatDisk. Michal, am I answering your question?
Yeah, just for me to know, how would I know when to use one and when to use the other?
If you're constructing a confidence interval, you're going to use the first one here, confidence interval. If you're trying to get a sample size, then you use the sample size determination menu. So it depends on what you're going to ask. Well, let's look back at what they're asking you for. In this one it says, assume that nothing is known about the percentage of passengers. Let's see. All right, so the key thing here, it says, and I was looking for it, it says, how many randomly selected passengers must you survey? So that's asking you how big of a sample size should you take. That's in contrast to this one, it says construct the confidence interval. So we're doing something different with that problem. We found the confidence interval as opposed to finding how many passengers. Ethan?
So you basically just use this if we want to find n.
Yeah, use that second one that we just finished with if you want to find n.
And then confidence intervals for margin of error.
Confidence interval will help you find your margin of error and the confidence interval itself.
Yeah.
Now sometimes, depending on the need or the source or the whim, sometimes instead of doing your confidence interval like this, here to here, what you'll do is you'll write 0.257 plus or minus 0.035. That's essentially saying the same thing as what we have up here. It's just that you're not showing these numbers explicitly. It's a matter of preference. The nice thing here is that you can see the p hat. That's your point estimate, and you know how wide the confidence interval. The nice thing here, 0.2221 to 0.2921, nice thing here is that they've already done the arithmetic for you. You can see what's the lower limit, what's the upper limit. So it's a matter of preference. Sometimes you could be asked to go from one to the other. If you are asked to go from here to here, what you could do is realize that the width of this confidence interval is really 2 times e. Because you go e minus and then e plus. So the width of that is going to be 2 times e. So if I needed to figure out e, I could say, well, 2 times e is 0.2921 minus 0.2221. 2 times e is going to be 0.0700. Divide by 2 on your calculator. Then you get e is 0.035. If you wanted to figure out what p hat is, p hat's in the middle. How do you figure out the middle of two numbers?
Add up, divide by 2.
Yeah, add up, divide by 2. So 0.2221 plus 0.2921, add them up and divide by 2. And that'll give you your p hat. So if you needed to go from this to that, you could. I'm not sure it's a problem that attracts me much, but in case you see it in your homework, at least you've seen it once here. Good questions. Anything else? All right, let's put this one to rest.